Alright, next problem is problem 51 in the book, chapter 5. Pause the video for a sec so you can read the problem before you watch me do it. And this is a double dot problem, but it's not too bad. Alright, I'm going to just jump right in by drawing free body diagrams for each block. Remember, we're going to do them as separate objects. This is M1, mass 1. So we have gravity, and I'm going to call it FG1 because this FG is going to be different than the FGs here. So if I call them all FG, then that technically means that they're all the same, which is not true. I'm going to call this FN1. And we have, according to the diagram, a rope pulling on the block this way, and we'll call it FT1. And now M2, another block, gravity pulling down, FG2, normal pulling up, pushing up, FN2, a rope pulling this way, FT2, and a rope pulling this way, FT1. If you remember, if we have an ideal rope, the tension in the entire rope is the same. So if the tension pulling here is FT1, this one pulling back with the same rope has to be the same strength, same tension. And block 3. FG3, FN3. This is tension 3, tension 2. Hey, look at that, we're done. Not too bad, huh? What's next? You guessed it, net force equations. F net y. Well, let's think about it. It's on a table. It's not moving up or down. So the F net in the y direction is 0. But we still want to list the forces. Excuse me. FG1. Sorry. Before I do that, because I'm thinking about what's positive and what's negative, let's define that. And like so. Up is positive, down's negative, right is positive, left's negative. Okay, so because of that, ooh, did you see what I just did? Negative. Because of that, Fn1 is positive, Fg1 is negative. But because it equals 0, Fn1 equals Fg1. By the way, this is useless for solving the problem, but because I'm using this as an example to teach you how to do this, I'm going to take the time to go through it. F net in the y direction is, again, 0. I should be labeling newtons. And that's Fn2 minus Fg2. And so Fn2 equals Fg2. And same here. Fn3 minus Fg3, so Fn3 equals Fg3. This is all in the y direction. All this tells us is in order for the block to not rise or fall, these two forces have to equal each other. As we're going to see, this does not help us solve the problem at all. Now let's do the x direction forces. F net x. It's going to be moving along this direction, speeding up actually because there's no friction. And so there is an acceleration. It's mass 1 times whatever the acceleration on block 1 is, F net 1, and that's going to equal, what are the horizontal forces? Just Ft1 in the positive direction. Over here, F net x is m2, a net That's going to equal the positive ft2 minus ft1. And m3 a net 3 equals ft3 minus ft2. Got it? ft3 minus ft2. We should also realize that since these are all linked together, what does that tell us about all of their accelerations? They have to be the same. So a net 1 equals a net 2 equals a net 3. So let's just call it A. M1A equals ft1. M2A equals ft2 minus ft1. This is making our life much easier. M3A equals ft3 minus ft2. And at this point, they tell us a bunch of things in the problem. For instance, M1 is 12 kilograms. So we'll just say 12 kg A equals ft1. They give us M2 is 24 kilograms A. And they don't give us any of these tensions, ft2 minus ft1. And they tell us that M3 is 31 kilograms. And they also tell us ft3, our pulling force, is 65 newtons minus ft2. What are we trying to find? We're trying to find in part A the acceleration, A. And so, how do we do this? Well, we can, we know ft1. Basically, we have, these are the equations with which we are dealing. This is how we're going to get any answers. And if we're looking for A, we got to figure out how to mix and match these together. Here, I see three variables, A, ft2, and ft1. When I see three variables, I think, I don't like you. Too much unknowns, right? Over here, we see two variables. That's a little better. And over here, we see two variables. Typically, if you have two equations, you're able to have two unknowns and still solve it, be able to solve it. So in order to solve this, we need three equations, which technically we do. So this is definitely solvable, but it's just how do we approach it? Well, this looks the simplest I've found in life, in physics life, I should say. Starting with the simplest, not always, but often leads to the right results. So let's just take that as an intuition and run with it. We're solving for A, so we want to have A. We don't want to get rid of A. So I like the equation written as it is. Basically, we can take ft1 and substitute it over here. We can't substitute it here because there is no ft1. So that's what I'm going to do. I'm going to take ft1 and substitute what it equals into here. So 24 kilograms times A equals ft2 excuse me, minus 12 kilograms A, because that's what ft1 equals. And then we can combine these, so ft2 equals 24 plus 12 is 36 kilograms times A. Well, did that get us anywhere? Now instead of an equation with A and ft1, we have an equation with A and ft2. May not have gotten us anywhere, but in reality it did. Because what we can do is we can take this ft2 and plug it over into here. And all we're left with is A's, which is a beautiful thing. So let's do that. 31 kilograms A equals 65 newtons minus 36 kilograms times A. Let's combine our A terms, add 36 on both sides, and we get 67 kilograms times A equals 65 newtons. Divide the 67 on both sides. A equals 0.97 meters per second squared. That's the answer to part A, I believe. Find the acceleration. Yeah. And now that we know the acceleration, finding the tension 1 in part B is easy. We just plug the A back into here and solve for T1, FT1. So FT1 equals 12 kilograms times 0.97 meters per second squared, and that's going to equal 11.64 newtons. And FT2 equals 36 kilograms times acceleration, and that's going to equal 34.92 newtons. Voila! And that's problem 51.